Hello everyone, this is Mr. Hussein Wasabi, and today we'll be looking at an overview of tutorial sheet question coming from tutorial sheet 1 of physics 1 or 2 of second semester Mulungushi first year tutorial sheets. Alright, so this question was, or let me say, is based on what I was explaining in the previous video on deformation of solids. So we'll use the same concept to answer these questions. So I'll be summarizing some things so I don't waste much of our time. Alright, let's begin. So solutions. Speaking with the first question, so let's read first. The variation with extension x of the force F of the spring A is shown in the figure. So this is the figure, which is of our interest. The point L on this figure, on the graph, is what we call the elastic limit of the spring. So this is the elastic limit that we're having here. So if you look at the y-axis, you're having the force being measured in what we call newtons, and the x-axis, what is this? The x-axis, there was a minor glitch. There's a mistake here. You're having the extension times 10 to the minus 2 meters, like that. So whatever extension value you pick, say 2, just say times 10 to the minus 2. Yeah, so from that perspective, I can begin. So the first question is saying describe the meaning of the term elastic limit. So the elastic limit is simply just a point at which a material no longer experiences what we call elastic change. Elastic change, remember, is simply just the ability of a material to go back to its original shape and size when the loaded force that was attached to it is removed. So I was talking about a point at which a material no longer undergoes, or let's say no longer undergo or experiences what is known as elastic change. Yeah, simple as that. So that is what you call the elastic limit. Others would say that the elastic limit is simply just the maximum load that can be applied to a spring, such that the spring returns to its original length when the load is removed. Though I don't really, anyway, we can say that, but in a nutshell, we can just say a point at which a material no longer experiences the elastic change, because that is the limit. It's a limit. It's like a point at which if you apply the maximum load, that maximum load will be the only load that will make that material experience an elastic change. And exceeding that particular point, then that material will enter a deformed state, and the entire plasticity will not be experienced by the particular material. So we're just trying to look at the point at which a material no longer undergoes elastic change, or a point at which a material will no longer be able to go back to its original shape and size when the load that was attached to it is removed. Alright, I guess we've understood that. Let's move on to the second question. Is saying calculate the spring constant Ka of spring A. So it's Ka because the spring is named A. Alright, so remember, given a graph, like I said, the gradient of this graph represents the spring constant. So the gradient is simply the change in y over the change in x, which will give us the constant of the spring A. And in the y-axis, we're having the change in the force over the change in the extension. So let's just try and find Ka with this concept. So change in F over change in x. So that is what we'll use. So now let's pick 2 points. Let's say point A. I most like to pick the first point to be the initial point, which is 0, 0, which means x1 is 0 and y1 is also 0. Point B, what would be point B? Let's pick the first point, which is 2. So now remember, whatever point you pick, just say times 10 to the minus 2. So it's going to be 2 times 10, 2 times 10 to the minus 2. Comma, what would be the y-axis value? This one is just zoom in a bit. So if you look here, this is 2. If I follow it up, it takes me this side. So that's the value I'm interested in. Alright, so now, what is the value of one box here? So you can use just common sense. You know this is 2, which means half of this, which would be 5 boxes, will give you what? 1, isn't it? So which means that one box should be somewhere 0.2. Or you can say the first value, which is 2, then divided by the number of boxes. So the number of boxes from here to there is 10, and this will give you 0.2. You can use that point or concept as well. So you just count 5 boxes to know where 1 is. So 0, 1, 2, 3, 4, 5. So this point is where 1 is, 1.0. 1.0. And 1.0 is not actually 1.0 in, so I'm just put 1. Alright, so this is 1, it's going to be 1.2, 1.4, 1.6. So this point is actually just 1.6. Simple as that. It's going to be 1.6. So we take it back to what we're doing, which is finding the gradient. So the y value is 1.6. They don't need of us multiplying by anything. They're just saying that, okay, the force is what? In newtons. That's what they're telling us here. They're not saying that the force value is being multiplied by a certain value to be converted to a basic, or this is a unit we want. Alright, so we can now say constant A is equal to change in the force. So this is my x2, y2, change in the force. So I'm having 1.6 minus 0 over 2 times 10 to the minus 2 minus 0. If you compute this on your calculator, you will simply just have 80 newtons per meters. Because you know that on top you're having newtons and on the bottom you're having what? Meters. So remember the division is per. So you're having 80 newtons per meter. I hope it's clear. Alright, so moving on to the last question, which is saying calculate the work done in extending a spring with a force of 6.4 newtons. So you have to first look for the force axis. So the force axis is this side. This is the force axis, the y-axis. So we need to know where 6.4 is and see the shape we can have. Alright, so let's try and do that. So let's just zoom in a bit. So this is 6.24 here. So where 6.4 is, follow it all the way and bring it down like that. So that's what we're having now. So with that information, we can see what we can do now. So it's falling on 8. So now remember that the work done, in actual sense, work done is equivalent to energy, and the energy stored, the energy stored by spring graphically is the area under the graph. So this energy is equal to the what? Area under what? Graph. Okay, so this means that the work done is equal to the area, and the area is equal to what? What shape is this? We're having this is the shape that we're having. So it's the shape that we're considering. This is a right angled what? Triangle, and the area of the right angled triangle is 1 over 2 base times what? Height. Now, if you look here, this is going to be 6.4 as your height. So the work done is equal to 1 over 2 times the base, which will be 8, times 10 to the minus 2, times the height, which is 6.4. Remember what I'm saying times 10 to the minus 2 because of the conversion factor given here. So work done is simply going to equal to, because if you compute this, you end up having 0.256 joules. And this is your final answer. So basically, when it comes to physics, it's all about you understanding how to apply the concepts that you have in order to solve problems that you might be given. Alright, I hope this is clear. Don't forget to like and subscribe. If you have questions, contact me on the number that is on your top left corner, or you can use the number in my description. Alright, my name is Mr. Hussein Mwasapi. Okay, remember, you're supposed to strategize before you become a statistic, and let's try and push for that A+.